So like example, like the for finding the chance here. And today I will just show one question, and I don't have any fancy technique here, but I would like to get help from people to think about this question. So first is the why the sum for the complexity about faster than others. I work on evolution basically in my lab. We try to understand how living organisms change and why. Or sometimes the question opposite. We want to understand why some of them don't change and also why. And a while ago, we become interested in some essential gene. And what the meaning of essential gene is that if you knock out this gene, and the cell will die, even though they are kept in a very normal condition with all required nutrients, the cell still cannot survive. And in general, a lot of essential genes are working very basic cellular function, for example, like DNA replication, transcription, protein translation. You can think about they are very important, right? That's why when you knock out a gene, they will die. And usually those genes will be shared between different organisms, because you can see the E. coli, you can also see the human cell. And lastly, we also know many human genetic diseases are caused by mutation in the cellular gene, so it justifies I can get a grant from the, well, our government support this kind of basic research. And if you look at the ESA genome, like the material I use, and about 80% of the ESA genome actually are essential genes, about 1,000 of them. And in general, people think because those are so basic and so important, so the essential genes should not change during the evolution. So they should be very conserved and evolve very slowly. So, however, we try to test whether this is really true or not in our lab. So the way we decide to do the experiment is we just find an awful lot from different species. That means like in different species, you can find a homologous gene. Like the ABC, they all have similar gene. And then we just, what we do is knock out the gene in the A species and put the ortholog gene into this and express it in the endogenous promoter. So the expression level is not a concern because we want to test the protein function. So only protein are different. Expression pattern are exactly the same. Okay, and then we can test if the essential gene basically they are working, so the cell will survive. But if they cannot work, the cell will become very sick or they will die. Very simple basic. And the system itself is we using body yeast, Saccharomyces cerevisiae as a platform, and we pick a few other yeast. They are separating from the cerevisiae at different time points. If you are human-centric view, we can imagine those different species. Basically, the distance, evolutionary distance is just like a human and monkey, elephant, bird, and fish. That's how far we push it. So basically, you can imagine what to put a fish gene into human to see whether the human cells still can survive or not. That's the idea. And of course, we cannot test all 1,000 genes because there's too many, so we decided to select some representative genes from different pathways, and we try to cover most of the pathways, and so we can have a better idea what's going on there. And also another idea is like that the single copy gene, because they are duplicate, then they become the function, so it's more difficult to test. In the end, we test around 90 genes. And then we just put all the ortholog to one back into this cerevisiae and test what happens. And basically, this is a summarized table. We classify the result into different groups. You can see what we call static means, no matter this gene comes from which species, they all work. So the mean function of the protein or interactional protein is completely conserved. They don't change at all. Of course, if they change at some point, like this point, and from there on, they become not working, we call this critical. That means like when they reach a certain distance, they become too different and they cannot work. And of course, we can also see some genes that only doesn't work in some species. That means maybe there's some species specific evolution happen there, and there will be interesting case. And the last category is what we call fast. That means no matter this gene comes from which species, even as close as this one, which is just similar between human and monkey, and essentially still cannot work, the cells still die. So we think this group of genes evolved super fast. That's why they cannot work anymore. And of course, if we believe the old hypothesis, we don't think we are going to find anything like this, right? Even this kind of thing would be rare because we believe all the essential genes should be static like this one. Surprisingly, that's the result we found. What we found, actually, the static one is only about 50% of them. And even more surprisingly, about 10% of them actually are working so fast, are evolving so fast. So what's going on there? So we look into the detail of those incompatible genes, and of course, you don't have to care about the gene name. You just look for this sentence, you can find they are involved in very general function of the cell, like ER trafficking, transcription, splicing, and RNA processing, things like that. They are all very general. However, those essential genes, they change so quickly, even when you get it from not so far away species, they cannot work. And more surprisingly, we found all those genes actually are the protein complex component. And what is protein complex? We all know that central dogma tells us the functional unit actually is a protein. However, we also know a lot of protein, they cannot work as a singleton. Basically, it's only for some enzyme and they can work by itself. A lot of protein, they have to work as a protein complex. That means they have to interact with other protein and then form a complex to execute the function. And in fact, the protein complex is very, very common. If you look at yeast, about 1/3 of a protein, actually, they are protein complex subunit. When you look at other eukaryotic systems, they are similar, between 1/3 to 1/4 of them actually are protein complex subunit. So protein complexes are not very rare. And also the protein complex, if they are in a large protein complex, they seem to have some chance to evolve quickly. And I don't think I have to tell you what the protein complex mean because we all learned this from biology book, a lot of protein like DNA polymers, like ribosome, they have to work as a big complex, right? And what we also found is actually, even though those essential genes are not working, but if you put the interacting partner into that from the same species, then they work again. This suggesting the incompatibility actually comes from protein interaction. And then, of course, you also know there are 50% of them are static. In effect, in this group of genes, there are also a lot of things that are in the protein complex. So right now, the question comes from why do some protein complexes evolve faster than the others? That's the question I will throw out. And actually, we don't have the real answer yet. So there are a few hypotheses we are thinking here is like we think maybe like during the evolution, the protein complex will start changing their composition. Even though they are working the same function, maybe they change a few of them subunits gradually, and that's why they may change quickly in some of them. And we also think maybe the interacting stability, or maybe the assembly order of them can affect their evolutionary rate. So basically, that's the idea we have now, and we are testing them one by one. And of course, I mean, what was sent here to give a talk, if I want some input from the audience, if you guys have some other idea you want to provide to me, then I will really appreciate it, and I will start here. Thank you.